Hello, everyone, and welcome to our 2021 Nuit Blanche presentation called The Art-chemist. My name is Alex, and I'm an instructor here at McGill University. And along with the many people you'll see presenting for you today, we're part of the McGill Chemistry Outreach Group. Aside from myself, most of the people presenting are graduate and undergraduate students studying here at McGill. The McGill Chemistry Outreach Group is a group of very passionate scientists that are volunteers here at McGill that are really excited to do chemistry demonstrations that are both educational and exciting to the general public. Our goal is to educate the public on chemistry and also to show how it's related to so many things in our everyday lives, and also to be able to understand chemistry and chemical terminology. In past years, we've done Nuit Blanche presentations here in the McGill department in our large auditorium, but unfortunately this year we had to move everything online. But that's okay, it didn't stop us because this is a great opportunity for us to show you chemistry experiments we otherwise couldn't do in the lecture hall. And furthermore, because we like to engage with our audience, we still have the opportunity to take your questions. So if you have questions, you can go to this website over here, or you can scan the QR code that you see over here. Furthermore, this website is also written in the description of this YouTube video. The theme for Nuit Blanche this year is art and culture. And throughout history, chemistry has played a very large role on both of these things. And the title of our presentation, therefore, is The Art-chemist. The way how we have this presentation structured is you're going to go on a virtual tour of our chemistry museum. And in fact, we're in the chemistry laboratory, and you're going to have a curator to guide you through different rooms in our museum. So Anne, who will be your guide, will get the whole presentation started off. So thank you very much for joining us. And without further ado, I'll pass it off to Anne. Enjoy the show.
Oh, hello there. I'm happy you found this statue which is a meeting point to start our tour of the museum. So my name is Anne, and today I'll guide you through our museum where we'll look at art, but we'll pay special attention to the chemistry that is behind many, many forms of art. So since we met at the statue, we'll start our museum by looking at the chemistry that is behind this statue. So without further ado, let's begin.
So we're going to do the golden dragon experiment in the fume hood. But before we do that, I want to give you a small intro. So before chemists are called chemists, we were called alchemists. And alchemy is a fascinating art, right? Alchemists are claimed to be capable of turning lead to gold. And we know in Game of Thrones, we see the birth of 3 dragons from the fire. So today we're going to show you how a golden dragon is born in the fire after taking a bath. So now let's switch the camera to the fume hood to my friend Laura. I hope everybody can see the fume hood. So first, we cut the dragon from copper sheet. So as shown by Laura right now. So the dragon has been pre-bathed in a mixture of salt and vinegar, right? You can see some dragons are inside. So I guess you already see the dragons really shiny after the treatment. So now what we're going to do is we're going to toss it into the hot spring on the heating plate. So it is actually, in fact, a mixture of sodium hydroxide, caustic soda, and zinc powder. Be careful because sodium hydroxide is also very, very corrosive and it will damage your skin. So we need to use gloves. So what is inside this hot spring? So the active ingredient in this mixture is called zincate. It is a colorless ionic form of zinc. So usually after approximately 10 minutes, the whole dragon will turn silver. So we already made one right before the show. And Laura is going to show you what it would look like after 10 minutes. So look at the contrast of color. So this doesn't mean we've turned copper to silver though. So in fact, what we have done is we have coated a thin layer of zinc on the top of copper, which is called a reduction oxidation reaction. I mean, since zinc has the silver color, so the dragon now looks silver. I guess maybe some of you already can see in the beaker, the dragon already starts turning silver. So now finally it is the time to turn the dragon golden. So what we need to do is we need to start some flame. And in the lab, you can see just on the left side of the beaker, yeah, there's a Bunsen burner, which is a common source of open fire. So Laura is gonna light it up. Okay, here we go. You see the blue flame. So what we're gonna do is we're gonna pass the dragon carefully on the top of the flame just to avoid overburning it. It takes some time, but I guess now you can already see the golden hue, right? From silver to gold. Yay, very fast, very fast. Fantastic. So I guess it's time to show you guys what are the color transitions. So let's give Laura a few moments so she can put all 3 dragons on the paper. Okay, almost there. And she's gonna turn the camera a little bit. So I guess now, can you turn a little bit down? Yes, that's fantastic. So actually, I think you can see now, it goes from copper to silver to gold. So I think now our question would be, did we just really turn copper to gold? I would say absolutely not. If you hear somebody claiming so, that is not right. He is lying or she is lying. So chemical reactions cannot change the identity of the elements. So copper will be still copper, zinc will be still zinc. What we have done was melting the zinc coating with the copper to make an alloy called brass. So this alloy is not hard enough to be used in armors, breastplates and so on. But because of its golden hue, as we saw, it is often found in decorative objects. And of course, it is also much cheaper than gold. Thank you very, very much.
Oh, look at that. So beautiful. Oh, hey guys. How are you today? Oh, I was talking about the mirror, of course, not myself. Hi, by the way, I'm Sing-Soo.
And I'm Chris.
And welcome to our demo.
Demonstration, yeah.
All right, so looking at this beautiful mirror, Chris, how are those exactly made?
Oh, so actually, if you think about a mirror, mirrors, they're made by having a very thin layer of metal on the surface of a glass. So today we're going to show you how to use chemistry to make a glass, to make a mirror with this flask.
Oh, very interesting. I didn't know they were made with metals. So metals like silver, however, I thought are metals. They are colored, right? But the silver resolution we have is transparent. So is this right? Is this silver, Chris?
Oh, actually, when we dissolve metallic silver into the solution, we transform the metallic silver into ionic silver by taking 1 electron away from the silver. And here today, we'll give that electron back to the ionic silver, so it becomes shiny again. So we will be doing this by mixing a solution here. This is solution containing silver with a solution of glucose and solution of sodium hydroxide. So we'll mix them together.
All right, so let's mix them together. I'm getting excited. So this transparent liquid is going to become silver?
Yeah.
All right. Oh, immediately you can see that the color of the solution has changed. So
as a matter of fact, metals, they can have different forms, just depending on how many electrons they have. So we call this the oxidation state. And the oxidation state of silver in the solution is +1. Therefore, it's missing 1 electron. So here, when we react ionic silver with glucose, the ionic silver will take 1 electron from glucose and it will be reduced back to its metallic form on the surface of glass, and we will see a mirror. On the other hand, here this is the structure of glucose. Glucose is a sugar, And it is a very important molecule too. It's what our body uses for energy. So when silver is reduced to elemental form, the glucose is oxidized to gluconic acid. So as you can see here, this is pretty obvious.
The color is definitely changing, and in a minute, you'll see that the surface will become very shiny if it's not already shiny enough. See, compared to the top, it's already coated.
Oh, wow.
The reaction is almost completed. And now you may be thinking how long this silver mirror will last. And of course, it can get oxidized back to the silver +1 state. And when that happens, we'll lose the shine. This is what happens actually when silver tarnishes. Well, to prevent this, if we coat the back of the mirror with an inert substance, we can then prevent the silver from reacting with molecules on the air, which cause the silver to reoxidize. And when that happens, the mirror will last many, many years.
So now if we compare this mirror that we made with the real mirror, we can see that they're all very shiny, both very shiny. Yeah.
Yep. So here's a little gift for a late gift for Christmas for those of you who are interested. But thank you for joining us for our demo.
And enjoy the rest of the demos.
Thank you.
We've arrived at the rare book section. Did you know that there's actually a lot of chemistry in the process of ink making? So ink is made to last for a very, very long time. So books can be several hundred years, and we can still read the ink even after so much time. So let's open the book and begin a new adventure.
Hey everyone, I'm going to talk to you today about invisible inks. Invisible inks were first developed 2,000 years ago by the Romans and Greeks as a way to send private messages without today's technology like email and text message. And the first invisible inks consisted primarily of natural fluids such as lemon juice, urine, sweat, diluted blood, milk, and other plant juices. And they discovered that when these inks would be put on paper, they would actually be revealed after exposure to heat or acids. And since then, many other invisible inks have been developed, including more complex mixtures of chemicals. During the First World War, many types of invisible inks were used in an attempt to keep messages hidden from the enemy. And this spurred a search on both sides to find a universal technique which could clearly or quickly reveal any invisible ink. The Entente were the first to discover a new technique using iodine vapors, which I'm going to show to you today. Now, what I have here before me is a jar full of urea, a saturated urea solution, which is the main component of urine, since I'm obviously not going to bring urine into the lab. And I have a jar full of iodine. As you can see, there's solid iodine at the bottom. If you could see the contrast, you could kind of see that the glass looks purple, but this is actually a gas because iodine likes to sublimate or turn from a solid directly into a gas. Now, I have a piece of paper here, which I've written a message on. As you can see, it looks completely blank. But when I open the iodine jar, pop the message in. As you see, it starts to develop. Into a message shown here. Now, the reason why this works is because iodine likes to bind to areas on the paper that have been exposed to moisture, and it has a preference to binding to substances like urea. So after this, I'm going to hand it off to my colleague Yiting, and she's going to show you a simpler way to develop a invisible ink at home, which doesn't involve urine.
So I have a piece of white paper as well, right? Seems like there's nothing. So actually this is already a message pre-written using a solution looking like this. Oh, colorless solution. And obviously this is my magic solution number 1. And I'm not gonna tell you what it is until later. So in order to reveal the message, we need to apply my magic solution number 2. Here we go. Oh, it looks a little bit like dark orange. And I can tell you, all the ingredients I showed you so far, you can find them at home. So what we're gonna do is we're gonna take a tweezer. Oh, where's my tweezer? Here we go. And also I'm gonna use a piece of cotton to just dip some of this dark yellow solution. Okay. So, okay, just give me 1 second. So you see, it's now very, very orange. So what I'm gonna do is I'm gonna try to swipe onto, ooh, oh, I think something is written and, ooh. Just give it a little bit of time. It needs some time to develop. Okay. I think it's a little bit faint. But we have to wait until it's drier in order to see the message better. But you already can see something is written, right? So these red letters, and let's just maybe wait for a little bit, let it dry a little bit more. Okay, so we can see it gets darker and darker. So, okay, I think it's going there. I guess we can read now. So it's written, the magic show is on, with a quite ugly flask I drew. I'm sorry, I'm not a good painter. So of course, you're gonna wonder, what are these solutions? What are the identities of the 2 solutions I just showed you? So this one is made of actually 1 tablespoon of baking soda, which is called sodium bicarbonate by chemists, and also just some water. So around 100 milliliters of water, so around 1/2 cup of water. The second one, this looks like a bit of an interesting, look like some spice. I can tell you it smells very nice. It is actually turmeric. So what you need to do is just to use a tablespoon of turmeric, just kind of mix it, not dissolve it, actually, you see it's not dissolved. Mix it with the alcohol, so the rubbing alcohol you can buy from pharmacy. And this is your magic solution number 2. So now actually you can send secret messages to your loved ones at home without using urine, of course. Okay, thank you very much. I hope you enjoyed it.
Yeah, thank you guys.
Hello, everyone. I am Detective Becca. So you have just received a secret message from someone, but now you want to know who sent you that secret message. One way we can do this is to look for latent fingerprints on the paper. There are many different ways to look for fingerprints depending on the type of surface. When we touch things with our hands, we leave oil and sweat from our hands on the surface of those objects. So one way we can look for fingerprints on paper is to use a solution called ninhydrin, which reacts with proteins that are found in that oil and sweat mixture from your hand. And I'm going to show you how to do that now. All right. So here is a potential piece of evidence. We are going to start by spraying it with a solution of ninhydrin. Now, we need to wait for this to dry in order to move on. So I'm going to use another piece of paper that I prepared in advance. The next step is to add a little bit of water. I'm just going to spray the surface lightly. And then finally, in order to speed up the reaction, we can heat up the paper. And you can see we are starting to develop a handprint. All right, voila, a handprint from our mysterious person. So now you can round up your suspects, compare their fingerprints, and figure out who sent you that secret message. Thank you.
All this talk about statues and books has made me really hungry. How about you? So we're just so happen to be in front of the Bistro Musée, which is our in-house restaurant. And here at the museum, we believe that food is actually art, and we frequently have culinary expositions to display all the art in food. So let's go meet the chefs.
So hello everyone, welcome to the Museum Bistro. My name is Dahlia and I'm a 3 Michelin star food scientist / head chef. And this is my lab mate and sous chef Nuit. So today we're really excited because we're gonna show you a cool crossover between food, which we all love, and chemistry. And in industry, chefs like to call this molecular gastronomy. And it's a cool way to introduce new textures, flavors, and colors to food.
Wow, these look so cute. Are they candy?
Sort of. It's kind of like a dessert. So inside, there's a fruit puree, and it's surrounded by a gel.
They look so delicate. Is it very difficult to make them?
Not at all. So it requires 2 very basic solutions. So first here, we have a sodium alginate solution. And then over here, we have our fruit juice inside a calcium solution.
I think I have heard of alginate. Isn't it from algae?
Yeah, it's derived from algae, which is very abundant and also good for you. And calcium, which is present in this solution, is present in a lot of food, and it's good for your bones.
So what do we need the calcium for, and what do we need the alginate for?
So essentially, what the calcium does when we add it into this solution is it helps the alginate coordinate around the juice sphere to create a gel, which we call a polymer.
Oh, wow, so cool. Can I try making one?
Yeah, go for it.
Oh, we have already frozen juice here. So I'll drop one to the alginate solution.
Yeah, go for it. So to make the process easier, we freeze the fruit juice ahead of time.
Okay.
And then when you drop it in this solution, you let it sit there for a few minutes so that the gel can form around the sphere. And then after that, we put it in a water bath to remove any excess gel, and then you end up with your final product. Do you want to break one?
For sure. Wow. Oh, so cool.
They're fun. I imagine that exploding in your mouth. Awesome. Well, we got lots more prepared for you here at the bistro. So on to our next course. I'd like to introduce you to my other amazing sous chef and lab mate, Kevin. Kevin, what do you have for us today?
Hey, Dahlia. Wow, that was fantastic. Now, how about some dessert?
Yes, I love dessert.
Does ice cream sound good?
Amazing.
Okay, let's make ice cream then.
Let's do it. How do we do it?
Well, normally ice cream is made by taking cream and sugar and cooling it down and then stirring it a lot. But I know of a faster way to do it through chemistry.
Cool. Show me.
Okay. All right, let me get my secret ingredient. I'll be right back. Ready for it? The secret ingredient is nitrogen.
Nitrogen, isn't that a gas?
It can be, but if you cool it down real low, it becomes a liquid, just like water.
Cool.
Do you know how cold this is?
No, how cold does it have to be?
Minus 196 degrees.
Oh my goodness.
Yeah. Okay. Let's. So normally you can add cream to it and just stir, but let's make some fancy ice cream. Do you like Dippin' Dots?
I love Dippin' Dots.
All right. Let's make Dippin' Dots.
Awesome.
All right. Before we do that, I have one cool trick to show you.
Cool.
Stick out your hands. Did that hurt?
Not at all.
Do you know why?
I have no clue. Tell me.
Okay, well, it's because you're really hot relative to liquid nitrogen. So before the liquid nitrogen hits your skin, it evaporates and turns to gas. So the layer of gas protects your hand. It's called the Leidenfrost effect.
That's so cool. I feel like a superhero.
All right, I won't delay any further. Let's make some ice cream.
Yes.
All right, that should be enough. Thank you. Let's get some raspberry. And some mint. I'm sure this one's controversial.
So is it problematic that we're generating so much nitrogen gas?
No, actually, because guess what's the main component of air?
Well, now I'm going to guess nitrogen.
Nitrogen, yeah. So once this evaporates, it just kind of all goes into the air.
Nice. And inside here, we just have cream sugar?
We just have cream and sugar, yeah.
Nice. So there's no additives like commercial ice cream?
No additives. All right. Boom. Look at that.
Beautiful. Can I eat them?
Yes, you can. I'm going to let you enjoy that off camera.
Thank you.
Ooh.
Well, I don't know about you guys, but I could sure use a drink. So now I'd like to introduce you to my other chef and lab mate, Ada. So Ada, what do you have for us today?
Did you say you wanted a drink?
Yes.
Oh, that's perfect because I'm actually a mixologist. I'm a chemist, but I'm a mixologist. So why don't we make Kevin a drink? Because man cannot survive on ice cream alone.
Thirsty boy.
All right. So what I've got here, if you could tilt the camera down for me, Kevin.
Yeah.
So I've made some special concoctions. Well, this one's not that special. It's just grape juice. But these things are sensitive to pH. Do you know what pH is?
Yeah, I think I know what pH is. I learned that in my chemistry classes.
Do you want to tell us?
Yeah, so pH is a measure of how acidic or basic something is.
So what does acidic mean? What do acidic things taste like?
Acidic things taste sour, like lemon juice.
Okay, and what about basic?
I don't actually know what basic things taste like.
Basic things taste really bitter, which is why you don't tend to see them too much in food. We don't really like bitter things. So things like dark chocolate, soap is basic.
Okay.
So I'm not going to put those in your drink because that, you don't want soap in your cocktails. But what I have here is just some normal old grape juice. I bought it at the store. You can buy it at the store too. And if I put this in here, it's kind of purplish red when it's neutral. And we say things are neutral if they're neither basic nor acidic. So like water. But if we add to this a little bit of a base, so something basic, it will turn bright green. So grape juice, it turns out, at a high pH, when it's basic, is actually green. So there's your drink. Do you want to drink it?
No, thank you. Can you turn it back?
You know what? Fair. Yeah, I thought it would taste good. I thought it would look good. It doesn't look that good. Let's try adding something acidic. See if we can change it back. Ooh. Okay, well, the lemon juice made it a bit cloudy, but there we go.
Actually, I'm not that big of a fan of grape. What else do you have?
I'm sorry, now you tell me you're not that big a fan of grape?
I'm picky.
All right, fine. Let's try. How do you feel about apples?
I like apples.
Who doesn't like an apple? So I made this special juice thing here out of apple peels at home. Waste not, want not. Let's pour some of this in here. And you'll see it's kind of clear. It's very slightly pink. And if we pour some base in here, because we can't just give you apple juice, that's not a very interesting drink. It turns bright yellow.
Ooh.
Doesn't that look good?
That does not look healthy.
What do you mean?
It kind of looks like
this, like the stuff we were making invisible ink with?
Yeah.
You know what? Fair. I was thinking Mountain Dew, maybe pineapple juice, but that, fine. It does look like pee. I'll give you that. Let me try one more time. One more.
Okay.
I think the problem is that I'm trying to make you all these nice things I made at home. You don't like me. You don't like the things I make. So this is some gin I bought at the store.
I'm a simple man. I
So
like gin.
it's called Blue Royale. Have you ever heard of it?
I think so. Is it Quebecois?
It is Quebecois. And they make it blue with the extract of something called a butterfly pea plant. That's hard to say. Butterfly pea plant. It's a purple flower, and it makes this blue extract.
Ooh, fancy.
And it's kind of cool. So if we pour some into a cup, it's beautiful blue color. Kind of looks like Windex. And what I'm going to add is just salt. It's called dry ice. So it's solid carbon dioxide. And it is going to have a really cool effect where as it reacts, it makes this amazing fog. But you can also see the color is starting to change. And
Fancy.
so it would continue changing if we were patient, but we're not very patient. So we're going to add a little bit of lemon juice just to help it along the way.
Okay, like a gin and tonic.
And so basically, as it becomes acidic, you get this beautiful purpley color. And it's kind of different than the blue. So what do you think? Can I tempt you with just some lemon, gin, and water?
Yeah, this is going to be my drink.
Finally. All right. Now I can finally go home. All right. Thank you so much for Kevin, for Ada. And I will pass you along now that you've had a drink, to the rest of your tour.
Cheers.
It's really cool to discover all the chemistry behind food. There's another very famous reaction that is in food chemistry called the Maillard reaction. Have you heard about it? You probably have, even if you don't know the name. So it's the reaction that happens when proteins and sugars react together at really high temperatures and gives the food a really characteristic taste. So this is what makes grilling steak on a barbecue so unique. Those dark lines on the steak are a really great example of the chemistry that happens in food. And that reaction also happens when you bake bread and when you bake cookies. So on a different topic, we're going to move on to our next exposition. But before this, here at the museum, we work on a lot of topics behind the scenes that we don't usually present to the public. But today, we're going to make an exception, and we're going to go behind the scenes at the art restoration room. And I just so happen to be in charge of this room. See you soon. Hello again. We've met before. So my name is Anne.
And I'm Mark.
And this is the paint restoration room where we really like to play around with colors. And we really like to understand the colors from their molecular composition. And once we really, really understand them, we're able to play around and have a lot of fun with the colors. So there's different ways to make colors. We can use metal, dyes, or make a complex formation. So let Mark take the lead.
So in this solution here, which is purple, it is potassium permanganate. And we've added a little base, sodium hydroxide, which most people would know is like drain cleaner or something. And we're going to add sugar to it, dextrose or glucose, D-glucose. In the base of this solution, we'll expose a functional group on it, an aldehyde, as you saw before with the structure of glucose in the Tollens experiment, which was the silver plating mirrors. So now we're able to actually change the number of electrons, the oxidation state of the manganese in the solution, which changes the color of it from purple to a green and finally to a yellow. And now, in this solution here, we once again have sugar and sodium hydroxide. Which the cork is capped on. And
We have a backup though.
so we've actually already made this solution and added the blue dye to it. Indigo carmine. And the glucose reduces the blue indigo carmine to this nice yellow color. And by reacting it with the oxygen in the flask, we can once again change the oxidation state, which gives us a beautiful red color. And then further shaking with oxygen gives us a nice green color. If we let the solution sit, it'll actually go back to red and to yellow, which is kind of like a traffic light.
All right, so for our last reaction today, we're going to form a color, but by reacting two chemicals together to form a complex that itself will give off a color. So we will react. In my first reaction, I have some starch that I will put in my big beaker, and we will give it a good stir. So we can see the red has appeared in the solution. In my second beaker, I have some iodate. So when I mix them together, it can form triiodide and form a color. So nothing has happened. This is because I have a third beaker, a third component that I need to add to my reaction, which is hydrogen peroxide that is used to drive the reaction forward. So when the triiodide is formed in the reaction, it can insert in the starch. And this reaction is unique because there are two reactions happening simultaneously. One that produces the triiodide that goes in the starch and produces the blue color, but also a second reaction that removes the triiodide in the reaction, and that makes it go back to a yellowish color. So this reaction is called the clock reaction because it oscillates between two colors. So we hope that you had a lot of fun playing with colors with us and that you understand them more and appreciate them in our art museum.
Thank you.
Hello, and welcome to our corner of the paint investigation room. Here, my partner and I will recreate pigments that were made hundreds and even thousands of years ago.
Did you know that the vast collection of artwork found in this museum was made using paints containing spices or even bugs?
In fact, for centuries, artists have been working to create the perfect pigments and dyes to achieve their paints using either natural sources or synthesis.
Today, we're going to begin by showing you turmeric. Turmeric is a vibrant yellow spice that is found in many of our favorite dishes. It comes from the plant Curcuma longa and has been used as a dietary spice and to cure human ailments.
Did you know that turmeric can also be used as a natural dye?
You see, turmeric contains a yellow pigment called curcumin. Today, we're going to show you how to extract curcumin to make dyes and paints of our very own.
Here, we first dissolve the turmeric in water, and then we add an organic solvent such as ethyl acetate. And when we do that, it'll separate into two separate layers with ethyl acetate floating to the top, and the curcumin will stay at the top with the ethyl acetate, and then the water and the rest of the turmeric will be at the bottom.
Curcumin is hydrophobic, which means it's water-fearing, kind of like oil, and it does not readily dissolve in water, which is why it goes into the ethyl acetate layer.
So here is just some curcumin that we've already extracted, and some swatches of paint that we just made in our paint investigation room. One of my favorite examples of red dye actually comes from bugs.
These dyes were first extracted by grinding up the tiny white specks on a cactus, and it found out that these white specks were actually bugs, as seen here.
These are small cochineal bugs. And as you see in our camera, these dried up bugs, when we start to grind them up, a red pigment starts to form. And then this red pigment will actually become more vibrant when we dissolve it in water, as shown here. It was found that the Mesoamerican peoples of Southern America actually had started using the cochineal bug as early as 2000 BCE. And then it was then introduced to Europe, where it was widely used in many paintings to dye, in many paintings and fabrics. And so here's a swatch of our paint that we used with an acrylic glue and the dye. And now my partner is going to show you a painting used in one of the brilliant red paintings made in Europe.
Is carmine still used in dyes today?
Actually, yes. If you head over to the bistro, you might actually find carmine in some of your favorite foods. It's used as a natural dye in ice creams, yogurts, candies. And then if you head over to the gift shop, you might find it in some of our lipsticks too.
Oh, wow. I didn't know it was found in so many things. Now, while these natural dyes are relatively simple to produce, the variety of colors is limited. For example, blue pigments are difficult to find in nature. Historically, they have been extracted from as ultramarine from the rocks lapis lazuli. However, this process is extremely expensive and time-consuming to produce the quantities required to make paints.
And this is where scientists enter the scene. In the 1700s, a German alchemist named Diesbach was trying to make a red paint using the cochineal that we just talked about. And this time, his red paint accidentally turned a beautiful, vibrant dark blue.
Diesbach had accidentally just created what would become one of the first widely used synthetic pigments for the color blue. But what happened? Why did his mixture turn blue?
Well, you see, his mixture was actually contaminated with blood. And when he mixed his original recipe, he accidentally created iron ferrocyanide, a key ingredient to making this blue color. And then he went on to call this dye Prussian blue. And do you know why he called this dye Prussian blue, Holly?
So the name Prussian blue originated in the 18th century when it was used to dye the uniform coats for the Prussian army. We're going to show you his optimized procedure for making Prussian blue using iron 3 nitrate and potassium ferrocyanide. First, both of these compounds are dissolved separately in water. So iron 3 nitrate is a purple powder and it becomes yellow, while the potassium ferrocyanide is a yellow powder that becomes colorless. When the yellow solution is then added to the colorless solution, the two compounds react to create a nice blue pigment. At the microscopic level, the atoms that are forming a crystal lattice with the iron atoms in different oxidation states, allowing for us to see this unique pigment. Prussian blue is the first of many dyes to be synthesized by chemists to form many different colors from readily available starting materials using simple procedures. This solution could be used as is, added to a binder, or turned into a powder as you saw before.
And you might be familiar with Prussian blue from some of the most famous artworks that you can find in certain museums. So this is the Great Wave, painted by Hosakai, which was a palette that did contain Prussian blue in it. And then Vincent van Gogh's Starry Night also had Prussian blue. And then, of course, we have artworks of our own that contain Prussian blue as well. So that concludes our little station. Now we're off to restore paints with the pigments that we just made. Thank you.
For stopping by.
All right. Thank you for this presentation on how to restore paint. So our last exposition at the museum is about special effects that happen in films and movies. And here at the museum, we really like our visitors to take part in the process of art making. Would you like to join us? So for this demonstration, Alex, who introduced the show, will be performing the reaction. So let's go.
Thanks for joining again. So over here, we're going to be doing one more demonstration. And to help with this demonstration, we're using this nice orange chemical called ammonium dichromate, which you see over here. We have these nice, beautiful orange crystals, and we're not going to use this product for its actual color. So we're not going to put it in paint, but actually chemistry itself can be a form of art. And chemists spend a lot of time being very creative at finding ways to make useful chemical reactions. And the chemical reaction itself can often be very interesting. So what I'm going to do is simply just light up and start a combustion reaction with this ammonium dichromate. So watch what happens when we heat up this ammonium dichromate. So we're forming chromium oxide. And as this reaction goes on, you can see it looks like a volcano. We actually call this reaction the volcano experiment. So special effects artists spend a lot of time working on different kinds of combustion and chemical reactions for special effects in theater and cinema. And this itself is a very big part. So you can just imagine how movies are a really big industry and a lot of people really enjoy it, including myself. So just to show how there's chemistry in lots of different types of art. Thank you very much for joining our show. We're going to end the presentation there, and hope you all enjoyed the chemistry that we did, and you learned something. And thanks for visiting us in the McGill University Chemistry Lab. And we hope one day for Nuit Blanche, or hopefully next year, you can join us in person. Have a good night, everyone.